Hello, how are you? Hope you are doing great. As usual, we're here to cover some few things in mathematics. This time around, we'll look at calculus. We'll look at calculus. For the sake of this topic, let's give it a code called, let's say, MTH 102, and that is calculus. M0102. That's the code for this course, and we say we're interested in calculus. Now, for us to be successful in this, I want us to list few topics that we will go through so that we'll have at least a good background of what we intend to do. Now, for us to be successful, let's say we will be looking at the following. First is function of a real variable. Function of a real variable. That's what we'll look at first. Now, in functions, there are some subtopics that we'll want to get used to, such as one, when is a relation said to be injective, when is a relation said to be surjective, and bijective. So in function, we'll be looking at when a relation is said to be injective. We're also interested in when a relation is said to be surjective. Then we'll be looking at when a relation is said to be bijective. We'll be looking at that. Now, after that, we'll also be looking at, still in function, we'll be looking at algebraic combination of functions. Algebraic, how to bring one or two or more functions, how we can add, subtract, multiply, or divide as the case may be. So we'll also be looking at, say, B, we'll be looking at algebraic combination. Algebraic combination of functions. Algebraic combination of functions. Now, after that, we'll be looking at piecewise functions. Let's call this one C. Piecewise functions. When a function is said to be piecewise, then we're going to consider when functions are said to be even and odd. Even and odd functions. Even and odd functions. Now we will still move ahead to look at the composition of functions. Composition of functions. We are also interested in looking at inverse functions. Inverse functions. Then limits and continuity of a function. That's G. We'll be looking at the limit and continuity continuity of a function, limits and continuity of a function. Then we will be interested in, which is a nice one, so let's call this one 2 in this case, where I will say differentiation, then 3 mainly integration. Now, for the sake of what we intend to cover calculus, I have said we'll be looking at these topics. At least these ones will enable us to understand what we intend to do calculus. Now, if that's true, let's now start with a function. What's the function of a real variable? What do we mean by function of a real variable? What do we mean by function of a real variable? What do we mean by function of a real variable? Now, I'm pleased to inform us that the idea of function is something that is known to all fields, all areas of life. Is known to and is very important to all disciplines as well. That of mathematics, physics, engineering, medicine, etc. and so on. So function is very important, and it is the basis on which calculus is also built. So as we move further, you are going to enjoy the beauty of what a function is. Now, having said that, we can give a precise definition of what a function is. Those of us that are interested, already we have said that is the basis on which calculus, when we say calculus, we are interested in differentiation and integration, is built. Okay? Now, what is a function if we want to really give a definition? I'm pleased to tell us that a function in mathematics is a rule. A function in mathematics is a rule. Okay? It's a rule or a relation. Let me write it. A function, this one we're going to use as function. A function in mathematics is a rule or relation, is a rule or relation that takes x values as input values into itself and outputs y values, or say f of x values as a function in mathematics is a rule or relation that takes x values as input values to itself and output y values or f of x value in a one-to-one one-to-one correspondence. Correspondence in a one-to-one. So we're saying that it's a machine, it's a rule, it's a law, or a relation, it's an equation, it's a mathematical expression that takes x values into itself as input values, and its output, after solving, it outputs y values or f of x values. Now this we can also demonstrate by having something like this. Assuming we say this, we are saying that it's a relation or a rule. So let's say this is a relation. This is a relation, and we can call it is some function, say f of x. Now we are saying that this one takes x values. It takes x values. Now these x values are the input values. Inputs. Input values. Now when it takes this, now in the end, into itself, then it will now output y values or f of x values. It now outputs y value. So is this kind of thing that we're trying to say is a function in mathematics is a relation, okay, that takes x values to itself, and it's after processing, it outputs y value in a one-to-one correspondence. Now, if this is true, then we can, in other words, say it's a mathematical machine. You can say this is a mathematical machine, a function. A function is a mathematical machine. It's a mathematical machine that takes x values into itself and outputs y values in a one-to-one correspondence. In a one-to-one. So we are saying that it's a mathematical machine if we take this as a machine, that it takes x values into itself. After processing, it outputs y values. Now let's consider an example. Let's consider an example where we have f of x is equal to 2x plus 5, where we have x is within the range, within this interval, say -2 and 2, where x is contained in this interval. Now, based on the definition that we are giving, we are saying that now this is f, this one is called f of x. This one is f of x, not f times x. This one is called f of x. Now, we are saying that f is a function of x. That's the meaning here. Now, f here cannot stand on its own. Okay? This interpretation here means f itself here, f here, cannot stand on its own, that it depends on x. So, in other words, for it to be a function, two terms are involved. One is a term that depends on another term. Now, this f here depends on this. meaning that f here cannot stand on its own. F is dependent. F here is dependent on x. Now, if x is dependent on x, meaning that x itself is independent. So these variables that we have here, f here is called the dependent variable, whereas x here is called the independent variable, which makes a function that this is a function of x. So if you see this side, where you will see that all the expressions this side is written in terms of the independent variable. Now this we can also liken to, as a human being standing here, my name is AMG, okay? Now, I am AMG because of one thing, and that thing is life. I cannot stand, the entity here cannot stand on its own. I am depending, for me to be alive, I need to depend on something. And the thing I'm depending on is life. Meaning that the container here, the vessel here, is depending on something. Whereas the thing that is depending on, which is life, is independent, because life can be on its own. But I cannot stay without life. So I can use myself as an example that I am a function, okay? And not just a function, but a function of life. And we can talk about me with life as time goes on. So not just a function of life, but also with respect to time, where you can talk about how many years as time goes on. Okay? So I am a dependent variable that depends on life and time. So I can use myself as an example as also a function. So when you're talking about a function, we have a dependent variable and we have independent variable. The independent variable can stand on its own, whereas the dependent variable cannot stand on its own. So I am a function of life. Now, example again, if you take life out of me here, you cannot talk about AMG again. Rather, you will be talking about the corpse. Same person, but you will be talking about corpse because something that the body is depending on has been taken away. Okay? So once you separate the two, this dependent term becomes a different thing. You call it corpse, you don't call it AMG again. Okay? Now I am AMG because of time, because of life that I am depending on. So this term is, so this is a function of x. So in moral, we are saying that f cannot survive without this. So it exists as a result of this term. So these other terms must be written in terms of this. Now, based on what we are doing, we are saying that x takes values in this range, meaning x can take -1, -2, x can take -1, x can take 0, x can take 1, and x can also take 2. So, meaning that the x values that we have here, let's try to do something here. Let's try to do something. Let's try to do something. The x values here that we have are -2, -1, 0, 1, and 2. That's what we have. -2, -1, 0, and 0, 1, and 2. Now look at it. Whereas this other side, we have a function. We have a function we say is 2x plus 5. Okay? Now let's see. When x, because we say these are x values. Now when x takes 2, what happens? What happens? When x takes -2, what happens? You have 2 here. Now x is taking -2 plus 5, meaning that this one will give you -4 plus 5, which is equal to 1. It will be equal to 1. Then, if again x is taking -1, what happens? We are going to have x is taking x is taking minus 1. X is taking minus 1, meaning that we have, from this relation, we have 2 into minus 1 plus 5. Now, 2 into this, we are going to have minus 2 plus 5. And if you simplify this, you're going to have 3. That's what you have. Now, if we say let x takes 0, when x is 0, what happens? We have 2 into 0 plus 5. Now, this part will give you 0 plus 5, so that the end result becomes just 5. That's what you have. Then when x takes 1, what happens? When x takes 1, what happens? When x takes 1, we have 2 into 1 plus 5. 2 to this will give you 2 plus 5, which is equal to 7. That's what you have. And lastly, if x takes 2, what happens? We have 2 into 2 plus 5. And here we have 4 plus 5, which is equal to 9. Now you can see that when x is imputed into this relation, okay, this mathematical machine, you can see that it imputes 1. When x imputes minus 1 into this relation, you can see that it imputes this. When x takes 0, imputes this into this, the output is this. When x imputes 1, the output is 7. When x imputes 2, the output becomes 9. That's what we're saying. So we are saying that this is the statement that we are trying to give. That is a relation that takes in x values and imputes y values. Now, let's do something. The x values that we have, which are the input values, these are minus 2, minus 1, 0, 1, and 2. These are the input values. And the other side, the output values are 1, 3, 5, 7, and 9. These are the output values. Output values. Now, these input values are called the domain of the function. The domain is called, these input values are called the domain values. Whereas the output values are called the range values, are called the range of the function. So after that, we will not be talking about the input values and output values. Rather, we will be using the term the domain of the function and the range of the function. So based on what you can see that after imputing this into the machine, it gave birth to this. It imputed that. After imputing this, it gave birth to this. Based on what we have here, after imputing this, it gave birth to this. After imputing this, you can see that this is what we have. So this, you can also say this one maps this, this one maps this, this maps this, this maps this, and this maps. So these are the various ways they associate. Okay? So you can say the association. They are associated in this way, or you say they are mapped. They are mapped in this way. Now, these are the domain functions, whereas these are the domain values, and whereas these are the range values. So this is one of the. So based on what we have here, you can see that to every domain value, there is a corresponding range value. To every domain value, there is a corresponding range value. So this one that we have here is a function, and you can see that all the domain values here are mapped out. They have their own association. They are associated to a unique value in the range. So this that we have here is what we are referring to as a function. So in other words, we are saying that a function is a relation or a rule that takes in x values into itself and after processing it outputs the range values. That's what we have. That's what we have. And that's the function. And now this one that we have here, you can see that they map it, the way they are associated in a one-to-one corresponding. This one to this one to this one. You cannot see that no particular one in the range value is mapped to, no two values in the range values in the domain are mapped to one in the range. All of them have their own unique value. So this one we say they are in a one-to-one correspondence. They are in a one-to-one correspondence. One-to-one correspondence. Now, when a function, a relation is in this form, instead of saying one-to-one correspondence, we can also say the function, the relation, is an injective relation. Injective mapping. This one, provided is in this one-to-one, either we say one-to-one correspondence or we say the relation is an injective mapping. An injective mapping, or you say an injective function, as the case may be. That's what we have. Now, let's look at this one that we have here, this expression that we have, that we call the relation. Now, this relation that we have here, as we all know, is a linear function. This is a linear function. The function that we have here is a linear one. It's a linear one because the degree of the polynomial here is 1. The degree of the polynomial here is 1. Or you can say is if we try to plot what we have here, you can see that what we're going to have is a straight line. It's a line graph that we're going to have. Now, this one, generally we can have this as generally we can have this as the equation of the line. Equation of the line, generally we can have this as equation of the line. We can have this as equation of the line. Equation of the line, where we have y of x, or let's say this one is now f of x, as we have, is equal to mx plus c. Mx plus c. Where m here is the slope, and c here is the point of intersection on the y-axis. On the y-axis. This one is our slope, whereas that is the point of intersection on the y-axis. And what we have here now, meaning that our m, based on what we have here, our m here is equal to 2, whereas our c is equal to 5. So this is the general equation of a line. So if you plot a graph, what you are going to have is just a line graph. Now let's try to see if really what we're saying is true. Let's try to see if what we are saying is true. Let's consider a graphical representation of what we have here. These are the domain values. These are the f of x values, the absolute values. So the x values will be on this axis, which is the x-axis. Assuming here is the center, then we have something like this. Then what are the values that we have in the x? The maximum number is plus 2 and the least is negative 2. Meaning we have negative 1 here, negative 2. Yes, this is okay. Meaning here will be 1, here will be 2, and here will be 3 on the x-axis. Whereas on the y-axis, the maximum number is 9. So we can take our units here to be 2, 4, 6, 8, then 10. In like manner, we have here 2 minus 2 minus 4. But we don't need to go this one because we don't have negative values. All of them are positive. So with this, we can now plot. Now, what are the associations that we have? You can now, if we are writing them in terms of pairs, we have minus 2, comma 1. That's what we have. Then the other one is minus 1, comma 3. It's associated to this. Then we have 0, comma 5. We have 1, comma 7. Then we have 2, comma 9. 2, comma 9. So if we are plotting when it is minus 1, when it is minus 2, we have positive 1. So positive 1 is somewhere here when it is minus 2. So something here. When it is minus 1, we have 3. When it is minus 1, we have 3 something here. When it is 0, we have 5, meaning something on this place. When it is 1, it is 7. When it is 1, it is 7. 7 is somewhere here. And when it is 2, we have 9. When it is 2, we have 9. 9 would be somewhere here. So if you are using your graph sheet, you will see that what we have here, taking a line of best fit, you will see that we are going to have a straight line. We are going to have a straight line. A straight line. Those of you that have your graph sheet, and if you use a meter rule, you will see that we're going to have. And this one that we have is a function f of x is equal to 2x plus 5, where x is in this domain. Where x is in this domain. That's what we have. That's what. So you can see that that's a line graph. Now let's consider some association. Let's consider some association. Already we have said, based on the type of mapping that we have, as we check the pair, we have said this is a one-to-one corresponding, which is an injective mapping. Now let's consider another example. Let's consider another example. Let's consider another example. Let's consider another example. Now, in case we have a function, let's consider a function, say this is equal to x squared plus 1, where x is still in this domain. Where x is still in this domain. Now, with this, now what do? Now, let's look at it. This one you have, all the x values are here. X values are minus 2, minus 1, 0, which are the domain values, 1 and 2. Now, this is the relation that we have, which is equal to x squared plus 1. That's what we have. Now, when we impute in place of x, when we have minus 2, then meaning that we have minus 2 all squared plus 1. And this one will give you positive 4 plus this. This one will give you, just say, 4 plus 1, which is equal to 5. This is equal to 5. Now, if you impute minus 1, when x takes minus 1 into the relation, you are going to have minus 1 all squared plus 1. This one will give you 1. This one will give you 1, yes, plus this other one. All you're going to have 2. Now, when x takes 0, what happens? When x takes 0, you have 0 all squared plus 1. This other part is 0 plus this 1, so that you have 1. Now, if x takes 1, you have 1 all squared plus 1. This one will give you 1 plus this 1. You're going to have 2. And lastly, if x takes minus 2, 2, positive 2, you're going to have 2 all squared plus 1. Where this one will give you 4 plus 1 equals 5. So you can see that after imputing the domain values, these are the output values which is the same thing as the range. So based on the pairing diagram that I gave, we can also, in a similar manner, write this other one out so that we will enjoy or have a good view of what we are doing. Now, for the domain values we have said domain values. Domain values we have minus 2, minus 1, 0, 1, and 2. These are the domain values. And the range values are 5, 2, and 1. These are repeated, so we don't have to repeat it. So we just have this. Then you say these are the range values. The range values. So when we have 2, you see that 2 is mapped to 5, 1 is mapped to, minus 1 is mapped to 2, then 0 is mapped to 1, 1 is mapped to 2, then possibly 2 is also mapped to this. So this is what we have. Now this kind of thing, now what do we call this one? Is this a function? Yes, it is a function. It's a function because all the domain values are mapped out and they all have unique values, though not in a one-to-one correspondence. Not in a one-to-one correspondence, but all the domain values are mapped out. So this is also a function. This is a function because all the domain values are mapped out and they have unique values in the range. However, they are not in a one-to-one correspondence. But if you look at it, you see that all the range values are also mapped. All the range values are also mapped. Now, in this kind of case, we are saying that it's not injective. In the case where all of them have a one-to-one corresponding kind of mapping, we say it's injective. But in this case, being that all the range values are mapped, though not in a one-to-one corresponding, but for this one, being that all is a function because this side are all mapped out, okay, and all this other side is also mapped, even if it's not a one-to-one mapping corresponding, we say that this type of mapping is called a surjective mapping. This side is a function because already this side is mapping out. It would have been one-to-one if all of them are having one-to-one correspondent, but this one is not. You can see that 2 and these two, negative 2 and 2 are having one value. So this kind of, but having that all the range values are all mapped, we say this kind of mapping is called a surjective mapping. Surjective mapping. Surjective mapping. The first one we did, you saw that this one was having a unique in a one-to-one correspondence. We said it's injective, whereas this one is not really having a unique one, though. But then all these other ones are mapped out, and all the domain range values are also mapped. So this one is called a surjective mapping. This one is called a surjective mapping. It's a surjective mapping. So we have concluded that it's not injective. It's not injective, but it's a function because all the domain values are mapped out. However, this kind of mapping here is a relation. It's a relation. The relation is a function, and all the elements in the range are mapped, and this one we call it surjective mapping. Then now let's look at another case briefly. We have known when it's injective and when it's subjective. Let's quickly look at another case. without necessarily going through the computation, but let's just look at the pairing diagram for us to determine if it's injective or surjective, as we have seen. Let's consider another example. Another example, in this one, let's say this is the domain. We are not going through the computation stage, but we have 3, say 4, and 5 in our domain. And for the range, we have 8, 9, 6, and 7. This kind of thing where we have 3 is mapping to 6, 4 is mapping to 8, and 5 is mapping to 7. Now look at this one. This other one, you can see that all the values here are mapped out. All the values here are mapped out. All the values in the domain are mapped out. So it's a function. This is a function. This is a function because all the domain values are mapped out. Now when you look at this one, you can see that the mappings are also one-to-one correspondence. They are also having a one-to-one. This one has a unique one with one-to-one. This one, no two values from the domain is mapped to one value in the range. So all this one are in a one-to-one correspondence. Though there is a value that is not touched, that is not mapped. But even if it is, this one here is an injective mapping. It's a one-to-one correspondence. So we say this is a function. It's a function. This relation is a function and is also injective. This one is also a function and is injective. Injective because this one to this to this is all these ones are mapped out, making it a function. And for in the range, you can see that they all have a one-to-one. Though there is a term that is not mapped, but then all other ones are mapped and they have their own unique images. So this is also a function. So this one is an injective mapping. It's an injective mapping. Now let's consider it's an injective mapping. Let's consider another one, another relation to see if it's injective or surjective as we have been able to identify. Now, if we consider 0 in our domain, 1 and 5, if we consider this, then in our range, if we have 0, 2, 10, and 6, and look at the relation, look at the mapping, the association. 0, this to this, this to this, and this to this. Now, this kind of mapping, this is a relation, but now this kind of association, is it injective or surjective? Now, based on what we have learned, you can see that one element in the domain is mapped out 2 times, making this thing not a function. It's not a function. This is not a function. Because for it to be a function, all the elements here must map out once. But you can see that the first term here, the first element here, is mapping out 2 times. So this is not a function. It's not a function. It's not a function. So being that it's not a function, we cannot talk about it in terms of being injective or surjective. For it to be injective or surjective, it must be a function. It must be a function. Now let's consider another one quickly. Let's consider another one quickly. Let's consider another one quickly. Let's consider another one. If we have this as our element in the domain, then we have 0, 4, and 6, where we have this is coming here, this is coming here, this is coming here, and this is also coming here. Now, is this a function? This relation, is it a function? You can see that this relation is not a function because this on the domain, in the domain here, you can see that one element is mapping out 2 times, 3 times. Okay? one element is mapping out 3 times. So this one disqualifies it. So this one is not also a function. So being that it's not a function, we cannot talk about it in terms of being injective or surjective. Now, let me also give another one, which we have also done. I know we have done similar something, but let's also try to look at it. If we have, say, A, B, C, and we have 10 and 20. If this one comes here, this one comes here, and this one comes here. Now look at this relation. Is this a function? This relation is a function. It's a function because the domain values are mapped out once. Though in the range, 2 values from the domain are having one range value. But it is a function. It is a function. Now, if it's a function, what type of function is this? Is it injective or surjective? This one is surjective. For it to be injective, know that everyone will have their own unique, they will map in a one-to-one correspondence. But this one, 2 elements from the domain are having one range values. Okay, so one assignment. So you say this one is surjective. It's a function. This is a function first, then we're saying that is surjective. We are saying that is surjective. Now, let's consider one which I will say maybe the last one. If we have A, B, C, and we have 1, 2, 3 here, and we have this, based on what we have done, is this a function? Yes, it's a function. This is a function. This is a function. This is a function. Yes, it is a function. Now, what type of function is it? What type of association is this? Is it one-to-one or surjective? It's a one-to-one. So this is injective. It's injective. Now, I want to conclude by saying that, and being that it's injective, if you look at it well, you can also see that all the range values are also marked. All the range values are also marked. So a function, a relation that is a function, if that relation is also injective and at the same time surjective, because you can also talk about it in terms of being surjective, because all the range values are also marked. So this function, this relation that we have here is a function, is both injective and also surjective. So when a relation is injective and surjective, we are saying that that relation is bijective. If a relation is both injective and surjective, we say that then it is bijective. For it to be bijective, it must be injective and surjective. Where this one that we have meets that criteria. So we have talked about a function, the relation being injective, surjective, and bijective. For that of injective, we have said it must have a one-to-one correspondence. Okay, the elements from the domain must map at once to a unique value in the range. Now, for it to be surjective, it must be a function, meaning all the elements in the domain must map out but once, and all the elements in the range must also be mapped. When all of them are mapped, then we say that is surjective. Now, for it to be bijective, the relation must be a function first, then it must be injective and surjective. Then we say that such a relation is bijective. Such a relation is bijective. Now, based on what I have done here, we have seen that a function can be a relation. A function can be a relation, but not every relation is a function. A function can be a relation. A function is a relation, but not every relation is a function. So you can see that we were able to do all that. Now, um, these ones I was not able to plot the graphs as we did in the first cases, but I want the audience to also look at a case for me, and that is let's look at it, writing this as a pair, if you can understand what we are doing. If I have this, if I have this, if I have this, if I have this, I want you to tell me if that relation is a function, or, if that relation is injective, bijective, or surjective. Now, apart from that again, I will also want the audience, as we did for that of the linear situation, I will also want us to consider these examples. Example, by determining the shape of the graph of these functions. Example, determine the shape of these functions. Determine the shape of these functions. Number one, we have x squared plus f of x is equal to x squared plus 1, where x is in the domain minus 2, 2. We have f of x is equal to 1 over x, where x is contained in this domain. X is contained in this domain. Then we have, let's consider this, f of x is this, where the function is absolute value of x, where x is contained in this domain. In this domain. Let's also consider some sine functions. Say f of x is equal to sine theta, where theta is contained in 0 to 2 pi. And lastly, let's consider f of x, square root of x, where x is contained in 0, infinity. Infinity. Now, I want us to determine, what I want you to do is determine already the domain values are given. So determine the range, then plot the graph, determine the shape of this function. And in our next class, I believe we are going to continue with what I've done. Now, in summary, today we have said we're introducing a new course. The course where the course code is Maths 102. And what we're interested in this course is calculus. And in it, we've been able to talk about the function of a real variable. And in it, we'll be able to determine when a relation is said to be injective, surjective, and bijective. And also able to determine the graphs of some of the relations that we have. So in our next class, I believe we are going to do more as we have in our topic. Thank you and God bless you.